Today's lesson is on vectors and how they appear on the coordinate plane. So I'm first going to go through some definitions with you. First term is standard position. A vector that is in standard position has its initial point at the origin. The ordered pair representation. The ordered pair representation shows how far in the x direction and the y direction that the vector is going. So I'm going to graph some vectors on this coordinate plane, and then we'll go back to the definitions. So the first one, I'm going to put a dot at 0, 0, and then a dot at 1, 2, 3, 4, up to 3. I'm going to draw a vector here. So this point here is at 4, 3. Okay, and I'm going to label this point R, and I'm going to label this point O for origin. Okay, so this is vector OR. So vector OR is going 4 in the x direction, 3 in the y direction. So we can label this OR is the vector, and we use brackets to denote this, 4, 3. This is the ordered pair representation of the vector OR. So vector OR, we have the vector symbol, we're starting at O, going to R, and then there's our ordered pair. Equal vectors. Equal vectors are what they sound like. They will have the same magnitude and direction. Okay, so I'm going to add another vector here. I'm going to start at -3, -1. I'll call this point T. And then my next point is going to be at 1, 2. And I'll call this S. And draw a vector that goes from those 2 points. So this is vector TS. In its ordered pair, we're going to the right 4 and up 3. So it will also be 4, 3. So these are equal vectors, but they don't start at the same place. So OR and TS are equal vectors, and they both equal 4, 3. That leads us to opposite vectors, which will have the same magnitude, but the opposite direction. Okay, so I'm going to put a point here, call this V at 3, 1. And then a point here I'll call W is at -1, -2. And I'm going to draw the vector going from V to W. So vector VW is going back 4 and down 3. So its ordered pair representation is going to be -4, -3. So VW was -4, -3, which makes it opposite both of those vectors. Magnitude, or the length of the vector. So if I have some vector, we're just going to call it x, y. That means we have the x distance and the y distance, so all we're going to do is the Pythagorean theorem. So let's call this vector v. So the magnitude of v is going to be the square root of x squared plus y squared. Now we're going to have some different operations with vectors. So let's say I have two vectors, I'll call that x1 comma y1, and some vector b x2, y2. And then we're going to do different operations like adding. So if I want to add vector a and b, you simply need to add the x's and add the y's. Subtraction, we're going to subtract. Okay, the last one is scalar multiplication. So k is just going to be some constant, so we call that a scalar. And as you can predict, we'll just multiply the x and the y by that scalar. So we're going to find the magnitude of v if vector v is equal to 2 times vector 3, negative 2 plus the vector negative 1, 5. So first, I'll distribute the 2. So this one will be 6 and negative 4. Then we'll add the x's and add the y's. So 6 plus a negative 1 is 5. Negative 4 plus a 5 is a positive 1. So then the magnitude is going to be the square root of 5 squared plus 1 squared, which will be the square root of 26. Okay, so we're going to draw a vector going from the point negative 2, 3 to b, which is at 1, negative 1. We're going to name the ordered pair representing AB, and then we're going to find its magnitude. So we'll draw, starting at negative 2, positive 3. B is at 1, negative 1. Draw it. Should go through the origin there. The ordered pair. We're going from negative 2 to positive 1, so we're going 3 in the x direction. We're going from 3 to negative 1 in the y direction, which means we're going down 4. Then the magnitude will be the square root of 3 squared plus 4 squared, which is 9 plus 16 is the square root of 25, which is 5. Now we're going to talk about parallel and perpendicular vectors. And it's exactly what you think. Vectors that are parallel and perpendicular, perpendicular, but we have some calculations that we'll use in them. First, parallel vectors. Vectors who are parallel have the same or opposite direction. So I can have a vector here. If I've got it going in the parallel direction, those are parallel, or they can go in the opposite direction. Those are all parallel. They're not necessarily the same length, but they're going in the same or opposite direction. Mathematically, two vectors A and B are parallel if there exists some scalar k such that A equals that constant times B. If R is equal to negative 2, 5, and KR equals 4, negative 10, what is K? So we're looking for the number that we'd multiply this, that would result in this, which is negative 2, because negative 2 times negative 2 is 4, 5 times negative 2 is negative 10. Next, perpendicular vectors. the directions are 90 degrees apart from each other. Next, we're going to talk about the dot product of vectors. So product is multiplication, and there's actually three types of vector multiplication. There's scalar multiplication, like we already saw, where you multiply it by a constant. There's the dot product of vectors, which we're going to use for a very specific case. And then there's cross products of vectors. So we're not going to do those, and we're not going to get too involved with what the dot product is. But if you go on to Calc 3 course, you will learn a lot more about dot products and cross products of vectors. Okay. The dot product of a vector. So let's say we have some vector A, which I'm just going to call A1, A2, or you can do this with X and Y, and some vector B, which I'm going to label as B1 and B2. The dot product, okay, the notation is a dot. The notation for a cross product is an X, like in multiplication. It's a simple calculation. It's going to be A1, B1 plus A2, B2. There are many uses for the dot product, especially as you get to higher level mathematics. But for our purpose, if A dotted with B is equal to 0, then our vectors are perpendicular. Okay, so we're going to use the dot product. First, for the obvious choice, perpendicular vectors. Perpendicular vectors. If the dot product is 0, then vectors are perpendicular. So are the vectors x, which is 2, -5, and y, which is 4, 1, are they perpendicular? So all we're going to do is apply the dot product. So x dotted with y is going to be 2 times 4 plus -5 times 1. So 8 minus 5, which is 3. 3 is not 0, so these are not perpendicular. Are the vectors x, which is still 2, -5, and z, 10, 4, perpendicular to each other? So let's do the dot product. So we'll have 2 times 10 plus -5 times 4. So we're going to have 20 minus 20, which is 0. So these vectors are perpendicular to each other. Now we're going to use the dot product to show vectors are parallel. So we've already looked at a scalar being a clue, but now we can also use dot product. And I'll write down the process here. So the process for how we can use the dot product to find parallel vectors is to change one of the vectors into its perpendicular vector. And I think about perpendicular lines. They have an opposite reciprocal slope. So we're going to switch the x and y and make one of them opposite. That will create a perpendicular vector. Then do the dot product. Because if I'm trying to show two things are parallel, if they're perpendicular, if these two are perpendicular and these two are perpendicular, then they're parallel to each other. That's what we're going to try to show. So let's say I had a vector 3, -2, and I want to create a perpendicular. Perpendicular to this, I can switch the x and y and make the 2 opposite, or I can switch x and y and make the 3 opposite. So these would both be perpendicular to this vector. So So I'm going to give you two vectors, and you're going to decide, are the two vectors parallel, perpendicular, or neither? So first we have A, which is 3, -5, and B, which is 10, 6. So we're going to do the dot product. That's going to be 3 times 10 plus -5 times 6. So 30 minus 30, which is 0. So these two vectors are perpendicular. Okay, our new problem, A is -3, -6, and B is 1, 2. So let's start with A dotted with B. So we're going to have -3 times 1 plus a -6 times 2. So that's -3 minus 12, which is -15. So these are not perpendicular. So let's see if they are parallel. And you may look at the numbers and see. So I'm going to make one of these perpendicular. So if this is B, I'm going to make a perpendicular B. I'm going to switch the x and the y and make one of them opposite. So I'm just going to make a -2, 1. Or you could have done 2, -1. So now I'm going to dot A with perpendicular B. So we're going to have -3 times -2 plus -6 times 1. Negative times negative is positive 6 minus 6, which is 0. So these two are perpendicular, these two are perpendicular, which means these two are parallel. So our last example, we're going to find k so that the vector 3, -2 and 6k are perpendicular, and then we'll find the k that makes them parallel. So to find them perpendicular, we're going to use the dot product. So 3 times 6 plus -2 times k, we'll set that equal to 0, because if it's perpendicular, the dot product is 0. So 18 minus 2k equals 0. 18 equals 2k. So k is 9. Now we're going to do something similar with parallel. I'm going to turn one of these into a perpendicular one, and it doesn't matter which. I'll just do this one. I'll make this -k6, or you could do k -6, or you could switch this one, doesn't matter. So now we'll do 3 times -k plus -2 times 6, and set that equal to 0. So -3 minus 12 equals 0. -3k equals 12. Okay. So k is -4. So that is vectors on the coordinate plane and applying that to parallel and perpendicular vectors.